Hello and welcome to section 15.3, Introduction to the Second Law of Thermodynamics. Okay, before we talk about the actual second law of thermodynamics, we need to understand irreversible processes. Now, an irreversible process is simply something that goes from A to B, but cannot go from B to A. Well, at least not in the same way that it went from A to B. This cannot happen in an irreversible process. To demonstrate this, I have, as you can hopefully see, some dice organized into black, red, and white. Now, I can shake this up and now they're no longer organized. Now, it doesn't matter how much I shake this, they're never going to, on their own, go back to, they're never going to on their own go back to being organized. I would have to organize them myself. This is the heart of an irreversible process. Now, the second law of thermodynamics is split into two separate parts. The first part is that heat transfer occurs spontaneously from areas of higher temperature to areas of lower temperature, and never from areas of lower temperature to areas of higher temperature. Simplified, heat transfers spontaneously from hot to cold, but never from cold to hot. For example, if you had a bucket of boiling water and you placed it outside on a cold winter day, heat energy would transfer from the bucket to the outside world. But no heat energy would spontaneously transfer from the outside world into the bucket. Heat energy only moves from the hot object or hot area to the cold object or the cold area. Before we can talk about the second part of the second law of thermodynamics, we need to talk about heat engines. Now, a heat engine transfers heat energy into work. And work can be anything. It can be a push, a pull, anything that involves causing motion is work. Now, this is a diagram of a heat engine. Heat energy is trying to move from the hot reservoir to the cold reservoir, as we discussed earlier. But it passes through this heat engine, and the heat engine transfers some of this energy into work. Now, ideally, it would transfer all of the energy into work. If we could make a perfect engine, it would transfer all of this energy from the hot reservoir into work. But sadly, this is impossible. There will always be some heat energy transfer from the hot area to the cold area. That brings us to the second part of the second law of thermodynamics, which states it is impossible in any system for heat transfer from a reservoir to completely convert to work in a cyclical process in which the system returns to its initial state. And basically, what all that gobbledygook means is that you cannot have a perfect heat engine. Allow me to explain mathematically.
Algebraic!
So, the first law of thermodynamics states that the change in the internal energy of a system is equal to the heat transfer minus the work done. Now, since a heat engine is by definition cyclical, that means that it returns to the exact same state it was at the beginning. There shouldn't be any change in the internal energy of the system. So delta U should be equal to 0. This means that 0 is equal to the heat transfer minus the work, which means if you move the work over here, that work is equal to the heat transfer. And now the heat transfer will be equal to the amount of heat that was transferred out of the hot reservoir minus the amount of heat that went into the cold reservoir. The efficiency of a heat engine is equal to the work done divided by the heat transfer from the hot reservoir. And based on what I showed you before, the work done is equal to the heat energy from the hot reservoir minus the heat energy into the cold reservoir. Therefore, I'm skipping a step here, we can say that the efficiency is equal to 1 minus QC, the heat transfer into the cold reservoir, divided by the heat transfer from the hot reservoir. Now, efficiency is measured in percentage. So it's the percentage of the heat in the heat energy that is transferred into work. So as you can see from this equation, in order for the efficiency to be equal to 1, or 100%, QC, or the amount of heat energy transferred from the hot to the cold, has to be equal to 0. But, as we learned from the second law of thermodynamics, QC cannot equal 0. So, you can never make a heat engine that is 100% efficient. And that's pretty much all you need to know about section 15.3, Introduction to the Second Law of Thermodynamics.